So hello, everyone. Welcome to week number 13. We are back. Anthony Orkeeline is here. We are back with another fine edition of learning math and stuff. Anthony, tell me later because I'm on a different page already, and I want to start and not go back to that page. So here we go, chapter 23. Inferences on two population proportions. So it's kind of strange that the test was only 20. Wait a second. The test should include 23. Did we not do 23 yet? Did we never do 23? I thought we did all of the confidence intervals and all the hypothesis testing. No, we did chapter 23. Yeah, 100% we did. I'm looking at these. 100% we did. So let me see about the homeworks for those. Yeah, that's fine. Yeah, we did chapter 23. 100% we did it. I remember doing it. Excellent. Yeah, we 100% we did. Which makes it even better. Because that way, no review. That means we have 2 chapters to go, not 3 chapters to go. No, last week, I told you guys, last week was the review. To come into class and ask all of your questions. That was last week. We are not having a review today. We are moving forward. We are going to go to chapter 6, which is actually a relatively easy and short chapter. But I don't see any PowerPoints on it on the common resource site, which means we got to do it the good old-fashioned way. Okay. So the good old-fashioned way is by using the ebook. And it's actually an easy chapter. It really is an easy chapter. The reason why we skip 6 and we do it at the end with 25 is because obviously you need 6 for 25, but you don't need anything else for 25. I mean, you don't need all those other chapters that we've done, 15, 16, 20, 22, 23, all those chapters. You don't need any of them for chapter 6. Chapter 6 is way back in the beginning of the book. So it's a chapter that does not really require much prerequisite knowledge. It's actually really, really straightforward, which is really nice. So I'm going to share my screen here, and we are going to go to, someone texted something. They said, is there no way? Okay, talk to me afterwards. Let's do this now. So, I hit the wrong thing. So chapter 6 is probably, okay. Chapter 6 is on two-way tables. Okay, two-way tables sound a lot easier than I mean, they're easier than they sound. Okay, a two-way table is as follows, and it's best illustrated via an example. Okay, it's best illustrated via an example. So let's take a look at this example right here. It references table 6.1, so let's reference table 6.1. Okay, here we have this table on academic degrees by sex. Degrees conferred in the thousands. We have women and men. And then we have which degree they've earned: associate, bachelor's, master's, or a professional / doctor's. Okay. And as you can see in this two-way table, this is one way, this is the other way. As you can see in this two-way table, that there are 673 women who earned associate degrees, 1,050 women who earned bachelor's degrees, and so on. We can fill in the 8 cells of the table. The 8 squares of the table are right there. Do we all agree? It's very straightforward looking so far. In the margins, the right margin and the bottom margin, we have the totals. So this 2299 is the total for this row, all these women numbers added together. 1612 is the total for the men row. 1074 is the total for this column, and so on. Does that make sense? Yes, no, maybe so?
Yeah.
Total. What is 3911? 3911 is the total for either these two or those two, because at the end of the day, we're all really measuring the same thing anyways. Right? You with me so far, everyone?
Yeah.
Is everyone there? I'm not really seeing lots of response. I see a couple people say yes, but I don't really see lots of people acknowledging. So can we get more than the 3 people who have sent me messages? Can we get some? Okay, a thumbs up is good, but I'd love to hear. Yes, thank you. Come on, let's some thumbs up are okay. I want to make sure you guys are getting this, and just having complete silence back, it's kind of hard to work with. Okay, so um, so this is a two-way table. It's called a two-way table because it's one way, two ways. That's why it's called a two-way table. The marginal distributions deal with the numbers that are in the margins. Okay, so for example, if I, looking at the table, which is now gone, I don't know why they made it disappear, but if I say, what percent of women, sorry, what percent of the students in the table are women? Well, in that case, what I would do is I would go to my total, which is 3911, and I would calculate how many women there are. But they were so nice, they gave me how many women there are. There's 2299. They gave me that number, and all I do, as they did, is 2299 over the total value over 3911, and it tells me that 58.8% of them are women. Okay, because what they're asking is about everything. What percent of the entire number is women? The answer, 58.8%. What percent of the entire number are men? Well, it's going to be, of course, the remaining 41.2%. The marginal distributions deal with the numbers that are in the margins. Okay. Now, a more complicated question deals with what are called conditional distributions. Marginal distributions, the only thing that matters are the numbers that are in the margins. Conditional distributions are a little bit tougher. For a conditional distribution, we're going to ask something like, what percent of women got their associate degrees? Not what percent of all the people are women who got their associate degrees, but specifically what percent of the women got their associate degrees. So let's say I ask that question, what percent of the women got their associate degrees? In that case, what would be my ratio? Look back at the table. What percent of women got their associate degrees? What over what would be the answer? And what I mean by associate, I mean not something better than that, but only associate. Not what percent of the people were women who got their associate degrees, but what percent of the women did. So the answer is 673, because that's the number of women who got their associate degrees, over what number?
2299.
Which one is it going to be?
2299.
2299.
Correct. 2299. What percent of the women? When they ask something like what percent of the women, that means the universe for this problem, the things that I'm considering are the women. So I would literally, with my hands, I would cover up the men row because that is not relevant for the problem. The only thing that matters for that problem is the 2299 row of the row of women. And of those, 673 got their associate degrees. We call that a conditional distribution because we are conditioning it upon the condition that we're talking about the women. Does that make sense? Yes?
Yes.
Okay. So very, very straightforward, I think. Okay. And you can ask lots of questions, what percent of the women did this? Now, another question, just since we're here anyways. When I said what percent of the women got associate degrees, we said the answer was 673 over 2299. What if I changed the question to what percent of associate degrees were earned by women? Let's say I asked that instead. What percent of associate degrees were earned by women? What would the answer to that one be?
673 divided by 1074.
Excellent. In that case, the universe of the problem, the numbers that we're considering are specifically the associate degrees, and how many of the 1074 were women? 673. Okay. So far, very, very straightforward, I think. Okay. Very straightforward. Enough that really, I don't even feel like I need to do a major example because it's really, really basic. Simpson's paradox, on the other hand, is a result that on the surface does not make sense for a very specific reason. So let's look at this following example. And this is going to be basically the example for today. Do medical helicopters save lives? If somebody asked you whether or not helicopters save lives, just without any analysis, without any study, what would your answer be? Would your answer be yes or no?
Yeah.
Okay. I mean, you would think that they do. Otherwise, why would we use them? Okay. So accident victims are sometimes taken by helicopter from the accident scene to a hospital. Why? Because helicopters save time. Do they also save lives? Let's compare the percent of accident victims who die with helicopter evacuation and with the usual transports to a hospital by road. So here's some hypothetical data. We have the two possibilities for how we get there, which is helicopter or road. And then we have the two possibilities for what happens to the victim, either they die or they survive. We see that of the 1,100 road victims, we see that 260 died and 840 survived. And of the 200 helicopter victims, 64 died and 136 survived, correct? That's just what the math gives us. So let me ask you a question. What percent of the road victims survive? What percent of the road victims survive? About 80%, 840 over 1,100, something about 80%, give or take, let's say. Yeah, I have a calculator here, I can get better.
76%.
How much?
76%.
All right, so 80% was a good approximation, about 76%. And what percent of the helicopter victims survive?
47.
How much? I just didn't hear you.
47.
I'm sorry, you're cutting up. It's 68%. Is that what you said? 68%? I didn't hear. I don't think I heard 68%. But 68% is the answer to this.
136 divided by 200, right?
Yeah, that's 68%.
Oh, okay, yeah.
Okay. Right. So we see that a higher percent survive by going by road than going by helicopter. Didn't we say that it should be the opposite? Didn't we say that we expect more people to, helicopters to save lives? And why is it that more people, a higher percent survive by road than by helicopter? Well, it's true that there's a smaller sample size, but it's still a percentage, right? We still have a higher percentage survive for that one than the other one. What does frequency mean? Someone said frequency. What do you mean by that? Can you be more specific? Andrew, you said frequency. I'm not sure what you mean by that. Yeah, if you're here late, just let me know at the end. Hello, thank you. Hello. The amount of people transported via helicopter. Okay. So Anthony Arakelian gave me the correct answer. It's not the numbers. That's not the issue. What's the issue is that you have to recognize that the people who went by helicopter were in worse shape to begin with. Otherwise, they wouldn't have gone by helicopter, right? Right? They're already at a disadvantage when it comes to surviving by the fact that they probably have a more life-threatening injury. So it's a lot more, it's understandable why fewer of them survive as a percentage, because they were probably not going to survive anyway. Okay. Of course, you don't see that from the math. You have to, see that from a common sense perspective. Okay. So what is the reason? It says here, the explanation is that the helicopter is sent mostly to serious accidents, so that the victims transported by helicopter are more often seriously injured. Okay. So here's the same data broken down by the seriousness of the accident. We have serious accidents, and then we have less serious accidents. In the serious accidents, we see that 52% that went by helicopter survived versus 40% who survived by going by road, right? Someone said, if the question was posed, what percent of total helicopter victims survived, would we add 200 to 1100? No, because 1100 is road. Right? If the question was what percentage of total helicopter victims survived, then your universe is helicopter victims. And there's 200 of them. And of those 200, 136 survived. That will be 68%. So back to this question, we see that for the serious accidents, 52% survived by helicopter, 40% survived that went by road. So it does seem that helicopters do a good job. For the less serious accidents, what do we notice about these percentages? What's the percentages of survived who went by road? What's the percentages who survived who went by road? Anyone could do that for me, please? Yes, no, maybe so?
Would it be 20 and 80? Oh, wait, no, my bad.
Wouldn't it just be
The people
80,
who,
yeah.
the percent oh yeah, 80%, right? 800 over 1,000 is 80%, right? Correct. Very straightforward. And what percent survived that went by helicopter?
84.
84%, right? So notice something very interesting. A higher percent survive for less serious accidents that went by helicopter, correct?
Yeah.
No, Simpson's paradox is coming, Anthony. A higher percent survive that went by helicopter, right? Yes?
Right.
And a higher percent survive that went by helicopter for the serious accidents, correct?
Yeah.
But overall, a higher percent survived that went by road when we combine them together. When we look at the less serious by themselves, more helicopter people survive, a higher percent. When we look at the serious by itself, again, more helicopter people survived when we look at percents. But when we lump them all together, more road people survived. That's Simpson's paradox. Why is it that when we look at them individually, in both cases, serious and not serious, a higher percentage of helicopter victims survived, but when we lump them all together, a higher percent of road victims survived? Does that make sense? That it should be that way?
Yeah.
If we look at them, really, it does? Why? Because if you see it, then it's not a paradox to you.
Because like there's many factors that play into it.
Well, 1 second. Let's look at just the one factor that matters when it comes to math. Helicopter, higher percent for less serious. Helicopter, higher percent for serious. Put them together and road has a higher percent.
Yeah.
That's the paradox, which it probably says something here. Simpson's paradox. An association or comparison that holds for all of several groups can reverse direction when actually combined as a single group. This is called Simpson's paradox. Okay. If you look at them separately, group by group, one or some kind of association or comparison or pattern holds. But when you lump them all together, it flips to the other one. That is Simpson's paradox. It breaks the individuals into groups, right? And then each group might have one pattern, but if you lump them together, you get exactly the opposite pattern. And as you were saying, I don't know who who was saying, but as you were saying, why does this happen? Because there could be lurking variables behind the scene that we're not considering. There are, as you say, there are other factors. Now, in every math test that I've ever seen, it's always been conceptual questions for Simpson's paradox. Usually a multiple choice question along the lines of, what is the principle called that tells us that when you lump them together, you get the opposite effect that you would expect? And then you look at the multiple choice and you say, hey, there's Simpson's paradox right there, and you move on. And yes, so the question is, what causes Simpson's paradox? And it's not the sample size that matters, but it's the fact that if you look at the amount of road victims of 1,000 versus 100, that these percentages, while they're true as percentages, because the sample sizes are so different, what happens is that the individual information of each one doesn't transfer over very well to the whole thing because of the skewed sample sizes in comparison, for reasons that we really don't have to go into. There's really no need for it. But at the end of the day, that is, see, in mathematics or in science, when you have a paradox, it's usually a seemingly contradictory concept that, if you analyze it well, is not as bad as it looked. Not as bad. It's not as paradoxical as it looked, I guess is a better word. The paradox is not really there because you have to look deeper. Here's a very famous one. Has anyone here ever heard of Zeno's paradox? Anyone know who Zeno was? Not the princess warrior, but Zeno, the real Zeno. Anyone who know what Zeno was? Anyone even get my joke? Do you guys know who Zena is? Wow. Zeno, warrior princess, wasn't that like a TV show? You know, I don't know. Anyway, Zeno was a Greek philosopher. I know a xenomorph. That's like an alien or something. I don't know. What is that? I've heard that term before. I kind of feel like it's like those movies, those Prometheus or whatever it was called. I know Zeno from Dragon Ball Super. You're saying words that don't make sense to me. But anyways. So Zeno was a Greek philosopher like 2,000 years ago, 2,500 years ago, something like that. And he had the following question. He said, imagine that two people are racing. You might have heard this as the tortoise and the hare. Have you ever heard the story of the tortoise and the hare? You know, the hare is much faster than the tortoise. Yeah. So out of the gate, the hare starts running and it's like really running really fast, and takes a break and falls asleep. So the tortoise, overtakes him. So that's not exactly what we're going with. On the turtle. That's not exactly what we're going with. We're going to do it a little differently. Suppose two objects, people, animals, who cares, are racing, and one of them has a 100-foot head start over the other. So one of them starts, right? You have a situation where the first one is 100 feet ahead of the second one when they start. And you might say, hey, that's not fair, but the second one is faster. In fact, the second one is 10 times faster. So when the one that's in front travels another 10 feet, how much does the second one travel in the same amount of time, being 10 times faster? It travels 100 feet, right? So the second one has now caught up to where the first one was before the first one traveled that extra 10 feet. Now, the one who's 10 feet ahead travels another foot. When that one ahead travels another foot, how far does the one behind travel? 10 feet, which means the one behind has now caught up to where the first one was 1 foot ago. Then the one ahead travels 1/10 of a foot. If the one ahead travels 1/10 of a foot, the one behind catches up to where it was. Then 100th of a foot catches up to where it was. Then 1,000th of a foot catches up to where it was. Then 10,000th of a foot catches up to where it was. Then 100,000th of a foot catches up to where it was. And this can go on forever. So Zeno said, I don't get it. He goes, how is it that anyone ever catches up to anyone who's ahead of them if you can break time into infinitely many small increments? And in each one of those small increments, the one behind never can quite catch up to the one ahead of it. Then why is it that when you look at the race overall, which is of course what we do naturally, it doesn't work that way? When you break it up into infinitely many pieces, you get one result, but when you look at the whole thing, you get a different result. This was Zeno's paradox, a very, very famous paradox. And why is it called a paradox? Because nowadays we know how to answer it. It involves calculus, so we're not going to do it. But essentially, it is easily answerable, as all paradoxes have to be. Okay, a paradox is only a paradox until the explanation is clear. Anywho, for what you need to know is just conceptually, you have to know what Simpson's paradox is. Okay. This chapter is over. It's a very, very, very simple and basic chapter. The grandfather paradox. Well, the grandfather paradox is about going back in time, killing your grandfather. If you go back in time and kill your grandfather, then your grandfather never had you, or never had your father who had you, or your mother who had you, so you're never born. And if you were never born, how do you go back to kill him in the first place? But if you don't go back to kill him in the first place, then you are born. And if you are born, you can go back. But if you can't go back, then how do you do that? It's crazy. It's crazy. But, you know, that's the grandfather paradox. There's something called the twin paradox. You guys know about the twin paradox? 12 Monkeys. Now that's one of the greatest movies I've ever seen in my entire life. What a good movie. The twin paradox is the following. Two twins are born. One twin gets on a spaceship and travels around the universe at half the speed of light, 9/10 the speed of light, really, really fast. And, or your mom, Back to the Future. Oh, well, that's something else. And comes back into the future, comes back later. And what happens is that one twin is still a child when the other twin has been aged 50, 60 years. This is fact. This is not even a paradox. This is true. This is what happens. Now, of course, you can't really do this experiment because people can't travel that fast for the effects to manifest themselves. But we've seen it on a small scale. If you guys are interested in that, you can look up the twin paradox and general relativity. It's all from Mr. Einstein. You might have heard of this guy, Albert Einstein. He did one or two things. I don't know. He was, a little famous. But this is fact, and it's just amazing stuff. There's some amazing stuff out there, math, science, etc. It's all amazing stuff, and you should all live lives of religious fulfillment and whatnot. Back to the Future is an amazing movie if you want a time travel movie that's more comedy based, but if you want a time travel movie that's more that's just really a great, probably the greatest time travel movie I've ever seen, you should see 12 Monkeys. Some of the greatest acting. We think of Bruce Willis as, we like his movies, but as a great actor, that's not his claim to fame. But this is probably his best performance ever, and everyone in the movie. Brad Pitt is amazing in it, probably his best performance ever. And Madeline Stowe, who I don't particularly like, I think it was her best performance ever. And that should be your homework. I'm probably going to let you out early tonight just so you can all watch 12 Monkeys. I think that's fair because it's really just an amazing movie. Oh, Ryan, have you? Well, you've seen both, so okay. But I don't agree with you. But the name is 12 Monkeys. 12 Monkeys. I don't know if it's a Netflix or Amazon Prime or where. I don't know where you can find it. Very famous movie, 12 Monkeys, an amazing movie. And Ryan, I'm down for that 100%. Anyways, chapter 6 is very basic. Very, very quick, because it leads into chapter 25, and chapter 25 is the stuff that you're going to be tested upon. You're not going to be tested upon chapter 6 stuff. You're going to be tested upon chapter 25 stuff, which is based upon the chapter 6 stuff. So 6 is very, very basic. The 3 things that we talked about. I'm done for today. I have nothing else to say. Unless you guys have any questions, I'm going to let you go and watch 12 Monkeys. We have an hour left of class. I want you to watch 12 Monkeys. I'm going to allow you to go on and watch that.